Hello everyone. Now let's discuss the very basic element of circuit design, that is NMOS. So to start from scratch, let's try to identify the structure of NMOS first, and then we'll go into the device characteristics. Okay, so it's a 4-terminal device, and it consists of a P-type substrate. The NMOS itself means it's an N-channel MOS transistor, N-channel metal oxide semiconductor transistor, and it's built on a P-type substrate. And conversely, if you have a PMOS, which is a P-channel MOSFET, it's built on an N-type substrate. Okay, so it consists of a P-type substrate. Okay, it has got two isolation regions, one on the left and the right hand side. So for example, these isolation regions are actually used to differentiate between two different transistors. Okay, so if you have one more transistor which is sitting over here, and you have this transistor which is sitting over here, this isolation region will be differentiating or will be isolating these two transistor behavior or these two transistor characteristics. So anything which happens over here will not impact the functioning of this particular transistor. Okay, so it has got an isolation region. Next, it has got some N plus diffusion region, and you see the N plus diffusion region is been carefully placed in this area, and there is some amount of space that is being left over here, and there is another N plus diffusion area being placed over here. So these are all basically fabrication techniques, and why the structure looks something like this, we will be talking more about that when we actually discuss the fabrication techniques of an NMOS, but not in this one. So now just take it from me that this is the shape of the NMOS transistor, where you have this N plus source area and you have this N plus drain area. Okay, next these are basically called the source and the drain area, the source terminal and the drain terminal. I'll come to terminals in some time from now. Next, you have the gate oxide. The gate oxide is placed just over the P substrate, and the way you see it is being placed in a rectangular shape over here. It's being placed only in this area. There are various techniques called as etching techniques, where you actually you actually are able to get this kind of structure. So that will be all covered in the fabrication lectures, in the fabrication videos. Next, you have the polysilicon or the metal gate, which is just placed over the gate oxide, and this forms your gate terminal, the most important terminal of the device, which actually drives your P-type substrate, or which basically drives your NMOS. Okay, so you have the gate terminal, which is denoted by G. Let's denote it by G. You have the source terminal, which is at this point. Let's call the other one as the drain terminal. Okay, and let's call the last one, which is again an important one. It's called the body terminal. So this terminal, usually while describing a symbol of NMOS transistor, we usually don't denote this particular body terminal, because it's just not doing anything. It's grounded. But this is a very important terminal to understand the threshold voltage characteristics of this device, and I'll very soon come to that point where we understand the importance of this particular terminal. But in a nutshell, this is a very important terminal that has to be taken care while designing any kind of circuit. Usually it's grounded. When we'll move into circuits, we'll see that this terminal is usually grounded, but any potential which is being applied on this terminal tunes the threshold voltage, and we'll see how it actually does that. Okay, so this was the basic structure, and the reason I went a bit fast is because this might be known to most of you. So this was the basic structure of an NMOS device. A PMOS also looks something similar to this. It will be just an inverted form of this one. So for example, this will be an N substrate in case of PMOS. This will be P plus, and this will be P plus. Okay, and the rest all remains the same. Okay, so that was about the PMOS, but let's start with NMOS, and the converse of it just describes the PMOS transistor. Okay, so the most important thing, the most important topic that will drive all your SPICE simulations is the threshold voltage. So why I'm emphasizing on the term threshold voltage? Because when we do SPICE simulations, the terms which are involved in describing the threshold voltage of an NMOS transistor, those are models. Those are the ones that will represent your NMOS transistor. So I'll come to very soon how to we do that exactly. So for now, we'll just try to understand what is threshold voltage. Next, we'll try to understand the terms involved in the threshold voltage, and how do those terms model any transistor. So for example, threshold voltage, let's say we'll call it as VT. We'll call VT as a threshold voltage. Vt equal to function of x comma y comma z. So this function will now accurately describe your NMOS transistor. and the function x comma y comma z will introduce you to the very basic equation of threshold voltage, and there are even more complex equation of the threshold voltage that is present underlying the spice algorithm. But we'll try to introduce you to the very basic threshold voltage equation, or we'll call it as models henceforth for now. So let's try to understand what threshold voltage is all about. So let's go step by step, and let's go a bit slow over here. So we have, let's say, VGS, the gate to source voltage, is being kept as 0. Okay, right now it's all 0 because gate and source both are at same potential, so we'll take it as 0. We'll ground the other terminals. We'll ground drain, source, and the bulk. Okay, for the second step is to ground all of them. Now when we do this, you see this is a p-type substrate, this is an n plus area, this is a p-type substrate, and this is an n plus area, and this actually reminds us of the famous p-n junction diode. Okay, so whatever behavior we try to talk about over here, they actually represent the p-n junction diode characteristics, p-n junction behavior. So whatever happens in a p-n junction diode on the application of potentials at the either terminals of the diode, exactly the same behavior will be replicated over here. Only just that there are two back-to-back p-n junction diodes been connected over here. Okay, so that's so basic p-n junction diode. If we know the theory behind the basic p-n junction diode, things becomes very simple over here to understand the NMOS characteristics. But let's try to make it more simple over here. Okay, so now both the junctions are off. So this is off, and there is a huge resistance between both the junctions because everything is off over here. We haven't applied any potentials to any of the terminals. Okay, so everything is off. Your p-n junction, your channel has got very high resistance. There is no connectivity between the source and the drain, and nothing is conducting. So this is being called as source to drain resistance. Okay, now what we'll do is we'll apply a small potential at the gate. We'll apply a small positive potential at the gate to source and see what happens. Okay, so when we do that exactly, so if you apply a positive potential over here, it essentially means that this particular plate, this particular metal gate, it's all positively charged. Okay, by the way, if you see, this is a polysilicon metal, this is your this is the oxide, and this is your again p-type substrate. So this area forms an oxide capacitance. This forms basically an capacitance. This is oxide acts as a dielectric, and this forms as two different metals, two different metal sheets. So this basically forms a capacitance kind of thing. Okay, so when you apply a small positive voltage at the gate, this particular plate of the capacitance gets positively charged. Okay, and as a result of this positive charge, it will repel all the positive charges which is present over here. So when we say it's a p-type substrate, a p-type substrate consists of p-type charges in majority. So the majority carriers of a p-type substrate are all positive charges. The minority carriers will be the negative charges. But over here, if you see now, since we are applying a positive potential over here, it will try to repel all the positive charges which is present over here. Okay, so let's say there are 5 positive charges present over here. This potential which is applied at the gate terminal, it will push all of them towards the interiors of the p-type substrate, leaving behind negative charges. So once something left in an electronics world, in a substrate world, whenever something goes, it leaves something behind. So for example, whenever an electron moves, it leaves behind a hole. So in the similar fashion, whenever the positive charges move out of their place, it leaves behind negative charges, and there is an accumulation of negative charges because of this particular phenomena. Okay. So what we'll do is, since I'm running a bit late out of time and I need some more time to discuss this, in the next step, what we'll do, we'll try to apply more and more positive charges. We'll try to increase the gate potential over here and see what happens, and see how does this depletion region, there is a depletion region formation that is happening over here. We'll talk more about this depletion region, and we'll see what happens when we increase the gate potential to such a level that there is actually a conducting channel being created between the source to drain. So let's try to do all this in the next video. Thank you.